Hey everybody, I got a question about practice problem 5.2.2, and I have a feeling that some of you might still be working on section on Unit 5, so I thought I'd post this before I did anything on Unit 6. I will post something on that, but anyway, so practice problem 5.2.2 gives us this blue structure over here, kind of a right angle bar thing, and it's cantilevered off of a wall. That just means it's set in concrete over on this wall, so there's no rotation, there's no sliding or any movement of any sort at point A. All movement has to come out here in the bar. So we've got, and of course we're in static, so there is no movement. We're imagining this is a static structure. So we've got F1 at point B, which is L1 away from A. And we've got L2. C is L1 plus L2 away from A. And then turning a 90-degree angle, we've got point D, which is L3 away from A vertically. And then we've got F2 that's at this angle theta from the horizontal. So it wants us to find the resultant force and its angle phi from the x-axis, which we'll assume is AC. And then it gives us also these lengths as well as the angle theta and F2. It gives us that magnitude. And then it wants us to find the resultant force, its angle, and then it also wants us to find something interesting. It wants us to find the distance along AC, it specifies. So we're looking for a distance along AC at which the resultant force acts. So it wants to find out, okay, you can find the resultant force, you can find its angle, but where does it act along AC? And that's kind of an interesting way to put this question. We'll dive into that. So first, if you're doing this in Mathematica, which I'll do so that I can show you my work as we go along, we plug in all the givens, and I'll just hop through and hit Shift Enter to recalculate those. I'll post all of these notes. I'll just post this notebook on the website so you guys can look at it. We'll skip that for right now. So we're gonna first let's try and find the magnitude of Fr. So the resultant force is what I'm calling Fr. So to do that, we need to add all the forces in the x, add all the forces in the y together, and then we'll treat those like the two legs of a right triangle and do square root of some of the squares to get our resultant force from that. So in the x direction, there's actually only one force that goes in the x direction, and that's the x component of F2. So to get the x component of F2, I would take cosine of theta and multiply by F2. And remember in Mathematica, when you're using cosine, you've got your square brackets and you have to add this keyword degree to make sure that it gives it to you in degrees and not radians. So let's recalculate that. And then in the y direction, we've got two forces that act that way. We've got F1 is all in the negative y, and then we've also got F2, which has part of it in the negative y, and to get that component of F2 that is in the y direction, we'll take the sine of theta times F2. And some of you might be wondering why I have an absolute value call out here, and then a negative symbol right in front of it. That seems kind of silly. The reason being, as I was doing this, I was noticing that because just because of the way the sine function works, it was saying that my angle was negative, which was correct, or that my force was negative, and that's correct in this case because it's going down, and we've said that down is in negative y direction. But I wanted to be able to be sure that I was assigning that, and it wasn't just happening because of the characteristics of sine. So I took the absolute value of it and then put the negative in front to say I'm saying it's going negative. That's nitpicky. Don't worry about it. So let's recalculate this to make sure I got that. So negative 48 is the sum of the y component of F2 and F1. And now we can do the force result. We take the square root, and that, if you want to remember, is control 6. And then square root of the x direction squared plus the y direction squared. And then we'll reevaluate that, and we get 63.6172 is our magnitude of the resultant force. Great. Okay, so now to get the angle from the x-axis at which that's acting, we are calling that phi. We think about, again, we go back to the x and y components of this resultant force, which are the sum of the forces in the x and the sum of the forces in the y. We say, okay, if those are forming if those are the legs of a triangle, and the resultant force is our hypotenuse, then we should be able to find the angle between the x direction and the hypotenuse, right? Just using some simple trig. And so sine is opposite over hypotenuse. So the opposite in this case would be in the y direction. So sine is if you look here, sine is opposite sum of the forces in the y over hypotenuse, the resultant force. And we've kind of already solved and set this up, so we're going to do arc sine, because arc sine will give us an angle, and that's what we're looking for. And we have to do this funny business where we say slash degree so that it gives it to us in degrees instead of in radians, and this n will help simplify everything. So when we do that, we get this negative 49.233 degrees, which means that the resultant force's angle off the x-axis off of AC is negative. It's a negative angle, which makes sense. It should be, right? The resultant force, if you look at this force and this force and say, which way do I think that force is going to point? Well, probably down to the right. And so the angle between AC and the resultant force is going to be a negative angle. And it turns out to be negative 49.2. Negative 49.92, sorry. So now we need to talk about getting, we know what the resultant force is, we know what its angle is off of AC, but we want to know, how do I find the location of where that starts? Why doesn't it just start at A? Why doesn't my resultant force just sit at A and have no distance between A and itself? Well, we're not just talking about forces in this unit, we're also talking about moments. So if we stop and think about that for a minute, then if you looked at this and we're thinking about moments instead of forces, and we take our moment about point A, wouldn't F1 cause a moment about point A? You know, if it's pushing down like that, I would say that that's going to cause a negative moment, because it's going clockwise, right? It's going to cause a clockwise rotation about point A. And F2, a little bit more complicated, because we've got it's at an angle. It's not perfectly in the x or the y direction. But let's take the y component of F2 first, and it's going down as well. It's just further away from A. So if a moment is a force times a distance, that y component of F2 times L1 plus L2 is going to give me the moment about point A from that y component of F2. What about the x component of F2? Because, sorry, I should back up. That's going to cause a negative moment as well, similar to F1, the y component of F2. The x component of F2, of course, is the cosine of this angle times F2, and so that's the force. But what's the distance between the x component of F2 and A? It's not L1 plus L2. We want the perpendicular distance, so it's L3, right? So if I took the cosine of theta multiplied by F2, and then multiplied that, because that's my force, and then multiplied by my distance, which is L3, then that would give me the moment due to the x component of F2 about A. And that, in this case, that would cause actually a positive moment. And so if I sum all my moments together, then I have a negative moment from F1, a negative moment from the y component of F2, and a positive moment from the x component of F2. Well, once I just sum those up, then I have my moment. Now, what does all that have to do with where the resultant force acts along AC? Well, if I have a resultant moment, then I also have to be able to say that I still have to be able to say that that moment is caused by a force and a distance. And if I'm in resultant land instead of in component land like we have been, if I'm saying the resultant moment is equal to some force times a distance, probably saying that it's equal to a component at least of the resultant force times some, we'll call it the resultant distance in this case. So what part of the resultant force, we know that the resultant force is at an angle, right? It's at this angle we found up here, this negative 49. If you can imagine that, it's just somewhere along the AC there's a point, and the resultant force is headed down at this negative 49 degree angle. So which component of that would be causing a moment about point A? Well, probably the force in the y direction, right? Because if it's along AC, then can the x component of the resultant force cause a moment about point A? No, because it's in line with point A, right? So only the y component of the resultant force is going to matter. So imagining in our heads again, I should write this out. I'll just come down here and type it. The moment resultant is equal to force resultant times distance resultant. Sorry, it's a lot of resultants. But this force resultant, it's not going to be the whole thing. It's only going to be the y component, right? So I'll put that in parentheses, the y part of it. So if I know my moment resultant, we calculated all that, right? Up here, by taking all those forces times their distances and the component of F1 or of F2. We got that. Then I should be able to, if I have the moment resultant and I know the force resultant, and I also know the force resultant in the y direction, which is just our sum of the forces in the y, can I solve for this distance along AC? And that's a key. If it's not along AC, then it's more complicated all of a sudden. You know, we could have it going for on AD or something like that, but that would be a lot more work. So having it along AC makes things really nice. So I should be able to solve for that distance resultant, right? And you've probably seen what the key to doing that is here. So let's I didn't evaluate up here, sorry. Let's try that one more time. So let's plug these in and see if we got things right. If we did our force resultant at 63.617 and phi is negative 49.9233 and our distance is 2.149, we say grade, then Yahoo, we got it right. So hope that helped. Let me know if it didn't. Put a comment on the discussion board or just email me, something like that. Thanks, guys.